Basic AI demonstrations feel like magic, but for a business system to function autonomously in production, that magic must be replaced by rigorous engineering. Every interaction begins with tokenization. The system breaks your human language into fragments and assigns each one a unique numerical ID, translating words into the only format a machine can actually process. Those numbers convert into embeddings, mathematical vectors in high-dimensional space. King and queen cluster together because their mathematical relationships are nearly identical. These vectors flow through the transformer block, analyzing the prompt simultaneously to predict the most probable next token. Because these models are bound by high-dimensional probability rather than a fixed database of facts, the specific architecture you select defines the absolute ceiling of what your application can safely do. To build effectively, you have to choose the right brain for the task. Decoder-only models excel at predicting the next word for a fluid conversation, while encoder-only models are built to read entire paragraphs at once for surgical data classification. When the input and output look completely different, like translating a language or condensing a 50-page contract into a summary, engineers use encoder-decoder bridges to digest the complexity before generating the new format. These structural choices are codified in the config.json file. Dimensions act like the width of an information highway, defining how much detail the model holds, while layers represent the floors of a skyscraper where data is refined and analyzed. In early 2025, reasoning models like DeepSeek R1 proved that models could match the performance of the world's most powerful proprietary systems by changing how they learn from their own mistakes. Using group relative policy optimization, the model generates multiple reasoning paths for a single problem, checks its own work against a set of rules, and self-corrects based on which paths were most successful. Choosing the right architecture is only the first hurdle. The next challenge is the sheer physical weight of these models when they hit your hardware. Selecting a highly capable 70 billion parameter model is one thing, but loading it is another. Without optimization, these models can instantly exhaust the memory of even the most expensive enterprise GPUs. At baseline precision, every single mathematical weight in the model requires a large amount of memory to maintain perfect detail, making it impossible to run on standard hardware. Quantization addresses this by aggressively compressing those weights. By trading away a tiny fraction of mathematical precision, we can shrink the model's total memory footprint by 75%. This compression is what allows sophisticated reasoning to move from massive data centers onto a smartphone, running locally without draining the battery. Quantization is the economic lever that makes deploying sophisticated models to millions of users financially sustainable for a business. With a model running efficiently, the goal shifts to control. Engineers must constrain the system from generating toxic outputs without suppressing its reasoning abilities so much that it becomes useless. We achieve this through layers of alignment. Supervised fine-tuning teaches the model hard facts, while reinforcement learning from human feedback is used to guide its tone and empathy. To remove the human bottleneck, we can use constitutional AI, providing the model with a set of ethical rules so it can critique and rewrite its own responses in real time. Traditional software tests rely on fixed, predictable outputs, but probabilistic AI is different. To grade these systems, we use a separate, stronger LLM to act as a judge, evaluating whether an answer is semantically correct even if the wording changes. An aligned and evaluated model is ready for a production environment, but to automate business workflows, it needs the ability to take action. While a standard model is built to generate text, an agent is built to execute work. It doesn't just describe a solution, it initiates the transactions required to solve it. When an agent receives a request, it generates structured JSON. This code acts as a command, triggering external systems like your company's inventory database or shipping APIs. For complex requests, the agent uses dynamic planning to break a goal into a sequence of subtasks. It maps out dependencies, identifying which steps must be completed before the next can begin. In a multi-agent system, a central orchestrator delegates these tasks to specialized workers. You might have one agent optimized for financial calculations and another dedicated specifically to safety monitoring. These patterns transition the AI from a passive predictor into a system capable of managing its own multi-step execution. Deploying these systems requires new safeguards. If an agent hallucinates a parameter, it can trigger unintended database wipes or get caught in an infinite loop that exhausts your compute budget in minutes. To prevent this, testing pipelines use mocking tools. We intercept the agent's commands to ensure the logic is sound without allowing it to execute real financial transactions during the test. Reliability also requires stateful memory. By using an external database to store the conversation, we ensure the agent remembers its current task, even if the underlying server container restarts. Finally, we implement circuit breakers to kill any process that exceeds a set number of steps, and observability tracing to audit exactly why an agent made a specific decision. Mastering this stack, from the probability of the transformer to the orchestration of the agent, separates an AI experiment from a functioning enterprise engine.